Okay. Okay. So, শুভ সন্ধ্যা সবাইকে নমস্কার. Hello, good evening everyone, and a warm welcome to Kolkata R User Group's 13th virtual meetup. I am Samrit, lead organizer of Kolkata R User Group, and by profession, senior statistical modeler and art developer. So, our group is proud to be a diverse and inclusive community, welcoming from all everyone and all individuals from all backgrounds and industries. So whether you are a student, researcher, or professional, or simply curious about statistics, data science, and even art, we invite you to join our sessions, ask questions, and learn from each other. So if you missed out our previous sessions, do check out our YouTube channel. The recordings are available there. I will put the link of the channel, YouTube channel, and the LinkedIn page in the chat shortly. And do not forget to subscribe the channel to get the upcoming notification for our upcoming sessions, and follow us on LinkedIn to get all the updates. So without further ado, let's welcome today's distinguished speaker, Abhirup Moitra, who will enlighten us on the topic creating dynamic patterns with complex functions with R. So Abhirup is a young mathematician, researcher, and science communicator who blends rigorous theory with intuitive data visualizations. He is not he has some other uh, responsibility of the member of Cosmic Charade and the co-organizer of this Kolkata R User Group. He was there from the day one when we from the foundation of Kolkata R User Group back in 2024 in the month of March or April. So yeah, and he promotes accessible learning and advances computational and mathematical research through his personal channels as well as professional channels. So yeah, welcome again, Abhirup, and over to you. And thank you to be part of this community once again. And yeah, all the best for your future endeavor.
Uh, yeah. Um, Thank you for such a warm introduction, Shamrit. So, uh, it's perhaps it's been that 1 year that I'm going to give uh, uh, talk, or maybe going to take a session on R. Um, so yeah, actually, after postponing the last session with such a topic, so it's privileged, and I'm so overwhelmed that again I got a scope to present something. So, am I audible? Firstly, tell me, and please allow me to share the screen so that I can
Hey,
present.
I know you were audible.
Yeah.
Yes, you are able. Let to go.
Okay. 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 Fine. So I hope my screen is visible,
Yeah.
right? Okay. Yeah. So here's the full screen. Okay. Fine. Is it possible to minimize this at some point? Yeah. No. Yeah. Fine. So, let's just. Okay. Fine. So, yeah. I'll start going to present this topic, and I hope I'm audible properly. And after finishing the session, I would like to take the questions. In between, if you have any question, please drop it into chat box, and Shamrit, please convey the questions. I'll definitely answer after these sessions. Okay, so let me start with this topic. This is what we call that creating dynamic patterns with complex functions. So, what is dynamic patterns, and with and why do we do complex functions? So complex functions are not only central to mathematics or the mathematical analysis, but also it's a powerful tool while analyzing, um, or maybe generating the visual striking and intricate patterns. So why do we study pattern? That is the first question, or rather the dynamic pattern. So we study the dynamic patterns is a it's a fundamental aspects of understanding the world around us. And pattern provide insights into natural phenomena, with understanding the human behavior and even abstract mathematical concepts. So even if it is context to understanding the natural world, as well as the predicting the forecasting, some climate data, or maybe the directional data, and directional statistics as well. So also some optimizing the, I mean, complex functions, or to understand the human behavior and the social sciences. And yeah, art and aesthetics means, I want to mean that to understand, to portray the art of mathematics by making complex graphs, patterns for teaching aspects, or maybe just like playing with patterns or behavior, understand the behavior of complex mathematical patterns and the dynamics out there. And yeah, mathematical exploration, so and solving problems, like nowadays, I used to solve problem in the field of complex dynamics with this is what we call the Julia sets, Mandelbrot sets, fractal images, um those sort of things. And here, in this study, we also focus on the biological and medical research, like understanding the brain images, or maybe the the MRI scans of your brains, or or if you have if you have to diagnose some mm, problems in your health related cases. So we also take help of such a complex, understanding the complex algorithms and aspects of such a uh, aspect cases. So in such a study, we focus on how complex valued functions, such as maybe the polynomials, rational maps, and exponential forms, can create dynamic geometric patterns. And these patterns emerge through repeated functions, iterations, visualizations, and of modulus arguments, such a things. So and uh, such concepts like Julia sets, like intersections of art and mathematics, concepts such as Julia sets, Mandelbrot sets, and conformal maps, which if you study the uh, um, if you are have you ever understood something, the transformation, if in probabilistic realm, like some box Mueller transformations, there are linear transformations out there, a lot of transformations, such a thing. So conformal maps is one kind of transformations, or one kind of maps which preserves the angle. So we also study such a things. So yeah. So the aim is to provide a gateway into understand the how simple mathematical rule lead to infinity reach behaviors. Okay. So so we first, I would like to dive into some facts of which we call the harmonic tapestry, or maybe the idea of harmonographs. You can see here. But how do we actually, what do you mean by the harmonograph actually? So harmonograph is it's um, a device, you can say, or maybe um, it's a uh, you know um, understanding the patterns, or maybe to understand or working with some graphical knowledges out there. So the story behind this is enchanting the invention, that is a legend has it that the harmonograph's origin can be traced back to the curious minds of mathematics artists like seeking to explorations and the connections between mathematics. So and it is created in 19th century. So with this harmonograph, I mean, before going to understand the harmonograph and its idea, so we first need to understand the a little bit. I mean, recap the knowledge of simple harmonic motion, like a 12th grade knowledge, or maybe the perhaps the yeah 11th grade of knowledge, or maybe you know that what do you mean by the pendulum and stuff. So yeah, let's see the visualization. So it is what we the visualizations of simple pendulum animations I have made. So such a visualizations or such a motion is looks like harmonic motions. So harmonic motions, we can explain that if you take a string out there, and if you just take a ball, a heavy ball, and if you just pull from here, and it will, if you just, I mean, if you see the motion, it's like a periodic, that's tick tock, tick, something like this. So this is what I mean in a very you know uh, without any formal constructions or maybe the formal meanings. That's the motions look like and see. So yeah, and if you see the R code here, so I'm not going to run all this code here because it's all about computer simulations and it takes time to visualize. So I hope I mean it is visible, right, Shamrit? The visualizations and the code out there.
Yeah, it's visible.
Okay, okay, okay. So yeah, I hope all the audiences out there is able to see this. So here, I mean, very simple packages I have used here. So one is called the GG Animate. We are all known with this. I mean, familiar with it's a this package, and it's you know the the mechanism behind this, and also the magic this thing. So first, to understand, so these are the record packages, and these are the necessary libraries given over here, and how to approach towards the algorithm. So definitely, if you see the simple harmonic motions, there has to be an acceleration due to its gravity, which is 9.81. And I have taken, these are the parameters of the pendulums, okay? So you can see this. And here, I have taken initial angles of, uh, you know, that the strings out there. So there is a string and there is a, so I'm just pulling it off, and just and it goes on and on and on. These things it is nothing but the initial angles with the I mean the of the string. So yeah, I mean the unit is in radians definitely, and here it is the length of a pendulum. So this is just like a initializations. Uh, for these animations, I have taken time sequence parameters, and yeah, it's a 10 seconds of 10 sequence. So now here, what I have done is that for the simple harmonic motions, there is I have taken I mean make a functions which calculate the angular positions over the time periods. So it's a very simple. So we have taken all the data frames in the perspective of the time sequence animations, and uh, make I mean the heart of this things is like the sine and cos things, sine function and cosine functions. And yeah, that's how I have made the plot, and you can try these codes at your own time. And if you have any further clarifications, or you can email me definitely. So yeah, I'm not going to, again I'm saying I'm not going to visualize, I mean run the code and all this thing, because there are so many topics I mean out there that I'm going to cover, and want to show you guys that the beauty of such a things. That's why it's a beyond the scope, you know. Yeah. So yeah, here it's from the pendulum swings. I have taken some brush strokes with the help of visualization. So this is the one of the visualizations I have prepared by making a code. So first you just see such a visualizations that so basically harmonograph actually in physical meaning, if you just see the harmonographs. So harmonographs actually captured the imagination of the public, becoming a centerpiece of, you know, scientific, or maybe the scientific salons, like yeah, and its core are the principle of harmonic motion and the resonance, and this concept deeply rooted with the law of physics as well. Yeah, so you see, here is some computer simulated images which is inspired by the harmonograph's elegant movements. So yeah, if you just see this quote, this quote looks very abstract things, but nevertheless we can try to understand this. So just if you just go to the basic formalisms for a while. So I'll actually, this formalism is making for some other things, but I can make you understand with such a mathematical context how to visualize such a thing. So we have taken some amplitudes out there, okay, and we have some fx and if suffix x and if suffix y. These are the frequencies of the motions of some del x and del y's. So what we are doing is that we are trying to shape and traced out some sinusoidal motions of two dimensions here. So now returning back to this context out there, so we are taking some uniform distribution, rectangular uniform distribution, and we are taking all the samples out there, and and yeah. So we are taking, okay, we are creating some human imaginations, and the precisions of mathematical algorithms intervenes some boundless creativity. Okay, so in this simulated images you'll see, and here are some of the simulated images out there. This is the we witness the culminations of centuries of explorations of uh, you know where the harmonograph's timeless, and Allure finds new expression of the realm of pixels and code out there. So here actually nothing, just I am taking the samples out there. Okay, so by the functions of jitter, we are taking each and every segments out there, each and every points out there, and we are trying to make it very continuous curves. And yeah, and even each and every samples, and we are trying to make a functions and parameterize that function with the t, and that's how uh, x and in this x and y coordinates, like the Cartesian coordinates, we are plotting this beautiful brush strokes here. So in a same way, we do so because you know uh, there are some functions which create this such a oscillations, and here is a mathematical formulations out there. So the hardcore mathematics part I'm just removing, and we can understand but for this time being we can just enjoy the art of this such a aesthetics. And I'll not waste too much time here. But yeah, once speaking in terms of hormonographs, so there are some packages, particular packages we use, that is the DAPE tools, and particularly the DAPE tools, because I take help of GitHub repo, that is this Marcus Bolt's method. So these are the things, and the library method and ggforce, and these are the things. So every df1, df2, these vectors are taking all the datas and the parameters into one, and we are trying to plot each and every data frames by making a continuous curves at there. And you know, such visuals are quite I mean mesmerizing by my own findings. So yeah, so let's now I would like to formalize some I mean introduce some curves out there, so which is what we call the Lissajous curves. Okay, so yeah, so we shape such curves by traced out by sinusoidal motions of two dimensions, right? And a mathematical harmony in such emotions is to see that so first I would like to see such a visualization that this is the simple harmonic oscillators, so with some functions, and these are all sinusoidal functions with the different parameters out there. So here again I mean this SHO positions takes the T, A, omega, and phi, these parameters out there. So why we do so? Because to calculate the positions of harmonic oscillators. Okay. And yeah, as per this formalism we are going through. Okay. So we can definitely give some fix our own harmonic oscillators out there. So basic harmonic motions, that is a sine omega t plus some alpha or maybe some omega out there. So all these are I mean this omega is like a phase space, and yeah, I just want to yeah, phase of oscillator, phase, this phi 1 and phi 2 are the phase oscillator. I mean the phi 1 is for the phase oscillator 1 and phi 2 is the phase oscillator 2, and some angular frequencies out there, and all the amplitudes as well. And this df1, df2, and if you go to the previous slides, and all the df part, or the these are all the data frames which I have made, or the data stored here for the each and every oscillators, or maybe the each and every uh, uh, curves which I have plotted. And definitely we are grouping all the oscillators, okay, into a simple single plot, and that's how we are going to plot these things. So yeah, this red curves for oscillators 1, and the blue curves is for oscillator 2, you can see, right? So the insight behind this, that we prepare such a functions to calculate the positions of simple harmonic oscillators. So yeah. So again, for the parameters for the second, for if we look into the second part of this, uh, so this is we are taking the parameters t and a for the amplitudes. I mean time sequences out there. There are angular frequency according to the x coordinates, and we are taking the frequency along the y-axis too. So so each and strokes out there, or maybe the if you go to the, I mean the code part of two. So each and strokes and each curve is a testament to the harmonious interplay between the mathematics and aesthetics. So a delicate dance of the form of function that transcends the limitations of time and space as well. Now, I would like to focus on the Lysigius curves. It's unveils the I mean, so it's offer a plethora of intriguing possibilities beyond their initial creation. So the fascinating fact is exploring of overlaying the multiple curves with different frequencies, leading to a captivating array of the forms. So yeah, these are all coming from the package we run before that, the dev tools and macros and tidyverse, so many things, and also the you know uh, um, the GitHub access, which I have, the GitHub repo references, which I have taken. So yeah, so these sort of things is so this is one of the pictorial and mesmerizing view, and and experimenting on the uh, with the variation in phase and amplitude adds another layer of complexity to these overlaid curves. Excuse me. And yeah, all the whether it's adjusting the phase relationships between the oscillators to produce the stunning symmetrical arrangements, or the modulating the amplitudes to create subtle shifts in intensities. So here nothing but that we have taken two amplitudes, the play with the two amplitudes out there. Okay, uh, two different amplitudes. Okay, and there are some uh, you know uh, and we are adding all this amplitude and grouping all this amplitude to play with this curve. So though the making you the understand the mathematical mathematics behind this, or maybe the more rigorous mathematics, it's the beyond the scope. But yeah, one of the key notions is that uh, that manipulating the frequencies of the oscillators, which involved, and we can observe how these curves evolve and intertwine, and creating in order to create intricate compositions of oscillatory motions, right? So this is the one part of understanding that with the help of R programs, or maybe whatever programming interface you comfortable, you can visualize such patterns and to study their this dynamic things. So here I want to deal with another facts, another mathematical curves. So this is what we call Rickman's sequence, and the Rickman sequence uh, is a non-traditional and intriguing sequence, which is defined by the simple set of rules. So here we are trying to exhibit the complex and often surprising behavior out there. So this sequence offer a rich and ground for exploration. I mean, context of number theory as a. So here we can understand what is the mathematics behind that. So so this is what the sequations, how we form the sequence out there. So this sequence, okay, uh, is basically known for its unpredictable and non-repetitive nature, despite the straightforward rule governing its constructions, right? So it's not already in the sequence. Sorry. The sequence doesn't follow a simple or easily discernible pattern. Uh, so here, some of the properties I will just show you. So, but before this, let's understand what is the algorithms, how the algorithms work. So we take some initial steps, the initialization with a0 being your zero, and we take recursive steps where is the n being a positive for some positive n. Okay, we take that if this I mean the n minus 1 and my negative of n and this component and this sequence has not been used before. So okay, if it making a sense, so I can better make you understand with the constructions. So we take a0 first, you see, and a0 is 0 and a1 is a 0 plus 1, which is called 1, right? And then a2 is 1 minus 2, that is negative 1. This is not allowed since it is a negative. So as we are allowed to take the positive one, okay, so we are neglecting the negative one, and we go for the a2, that is 1 plus 2, that is the 3. And second, again, a third, that is a 3 minus 3, that is a 0, and already in the sequence. So a3 is 3 plus 3, 6. And we go like this. And what if we continue this manner, the sequence being as 0, 1, 3, 6, 2, 7, and so on? So this sequence is known for its interesting properties such as seemingly chaotic patterns of values and the fact that it often revisits the same values of different states. So, what are the properties and patterns out there? One thing is that non-repetitions, that each number and the sequence is unique, which emphasize the condition that no number should repeat. And yeah, the sequence oscillates. Definitely, the sequence oscillates, and we move both forward and backward as well. And by progressing in order to progress to larger values overall. And the sequence definitely grows indefinitely, but in the irregular gaps. Yeah, so we can see these visualizations out there, right? So I'm coming to the in the plotting. I mean the R programming facts. So first we can notice the plot out there. Okay, so the plot is like, so we can observe that the dynamic and seemingly chaotic natures out there, right? So of the sequence by plotting the sequence. So either on a number line or more artistic uh, forms such as the arcs connecting consecutive terms. And And yeah, one thing is notable, that is the forward and backward movements, which is creating a visual appealing patterns. So why not understand the I'm sorry, why not understand the, you know, the coding part out there. So sorry, yeah, so here it is the coding part, I mean the programmings and algorithms part. So here this functions sequence of recommend this thing. So this functions actually generates a recommend sequence up to a specified numbers of terms. Okay, so by calling the numeral, right? So here first thing is goes to initializations of x and y. Both are empty vectors to store intermediate and sequence values. Z is, so Z x and y both are intermediate and sequence value. So Z is initialized to 0 because in order to represent the first term of the sequence, and I1, this is a I mean is it's a loop counter starting from 1, right? And it's a basic while loop I have performed. That is, a loop runs until the I exits into the input numeral, right? And each iterations is a set to the current value of z, and I1, I equals to 1, uh, or I of y is a set to z directly. So as I being greater than to 1, the code actually check if y uh, y of I minus 1 and x, I mean, if you write that y of in suffix y of I minus 1, and if you take that vector x of I, so this is a positive and not already in y. So if true, and if it is true, we check the condition. If it is true, it says that y of I and to y of I minus 1, this thing actually, yes, this part. Okay, so otherwise it sets yi to the positive one. So first here, if true, if it is true, if this condition is true, okay, um, so it sets yi to yi minus 1 minus xi. So otherwise it sets yi to this thing. So I hope you understand this. And yeah, and the z and I are incriminated in each iterations, and we return the function actually returns a matrix combining x and y. And what is the plot? You know, yeah. So here, I just want to move into the plotting facts out there. So the functions actually, the plotting challenge out there. So we'll see. Okay. Yeah, plotting challenge. Yeah. So I'll go for the this functions, that plotting challenge. Now, if you just call this function sequence here recommend one, if you just write the 25, so it'll repeat up to goes on to, or repeats up to 25, 26, or maybe 100 times, 200 times, and so on. So yeah, so here the recommend sequence, while we are trying to retrieving the values out there. So what we do is that, and what is the algorithms behind it, that we input the parameter that is numeral, uh, there is a numeral out there, and it specifies the number of the terms to plot. Okay, so it generates the sequence actually to generate the sequence and retrieves the y values out there. So here the initializing vectors, that is the initializing vector. Okay, these are two initializing vectors, correct? And set to store the x and y coordinates for plotting, definitely. And the degrees is to these degrees are to uh, is a sequence from 1 to 179, and representing the angles for a semicircle calculation. So we'll need the degrees from 1 to up to 179 for the simulate the semicircles, definitely. That's why I have add this command out there. And yeah, and the loop here we have executed that for oh, one more thing is that numeral 2 and numeral 1, this represent the number of the arcs. Okay, number of the arcs we have initialized. And the loop, yeah. Now coming back, this loop, that is a loop through each pair of terms to calculate the coordinates arcs, and to calculate the radius of midpoint of the semicircle, whether the curves upwards or the downwards based on the parity of I. Okay. So it's all about evaluating whether that circle, I mean the semicircle, will curve upwards or downwards. And one more thing, that is, I believe that, yeah, not I believe, it's yeah, for sure, that heights and length calculation. So we calculate the y coordinates, which is by the alturas. Okay, okay, this. So exactly. So and the x coordinates as well by distance shears. Okay. So for the semicircle. So sorting out all the lengths, so we ensure the distance shears, the variable distance here is a are the correct order based on the direction of the arc. Okay. And to store all the coordinates, we store all the coordinates, that is the x coordinate and y coordinate, by this. Okay. Now coming to the plot, and so combining all the this x and y coordinate out there into a matrix, which is called the matrix Z, and we remove the duplicate points, right, to get this variable, I mean this vector. So the plot background, we set here the black, you can see, and plot the sequence with the white lines, definitely. And yeah, these are the call white, and means to do so. And we run the code. We call the we call the plot challenge functions. Okay, so this will, so if it is 100, so this will generate a plot showing the first 100 terms of that sequence with the arcs connecting the terms. Now, can I do using tidyverse? Yeah, the tidyverse makes these things more stunning. Uh, yeah, definitely. You go for the visual first. So here, the modern R package, definitely the tidyverse, particularly the deployer and ggplot2 to create the clean and effective visualizations, and we can break down uh, the the code out there. So here again, same initializations, the sequence as 0 first, and by the iterative process, that means, so for each subsequent index I, each subsequent index I, okay, compute a candidate value by subtracting I from the current value. So if the candidate is positive and not already in the sequence, it is added. Otherwise, add I to the current value. Okay. And the mathematical insight is like this process ensure that the sequence generates unique values as much as possible by balancing the between you know the subtraction and addition to explore new values. True. Well, and that's how again the radius calculations by constructing the arc, and here this things comes under the radius calculations. That radius is half the distance between two consecutive points in the sequences, and the theta values out there. Yeah, theta values out there. Every theta values you can see this theta value, these and rest of the things out there. It's a trigonometric function to generate x and y coordinates for the semicircle based on the calculated radius and center. So, what is the type of curve? The type of curve you will see that definitely you see that which alternates between upward and downward curves to create a visual appealing pattern. Now, here plot recommend these things. We plot the first n number of elements of the sequence. That means we create a data frame with start and stop points for each semicircle and determine the type up or down in the direction of the forward and backward of the each curve. So the construct arc here, sorry, yeah, this construct arc, this is a function to generate the paths for each segment. Okay. And we plot the semicircles using grammar of graphics 2 or the ggplot 2, which customizable parameters, right, for size, transparency, enhance the visuals. So, what is the key features we can see out there, or the plot if you see? So we have the gate recommend that this gate recommend if you see. So this gate recommend is to generate the first n elements. Okay, so gate recommend is like, oh, it's a function effectively generates the recommend sequence by leveraging the vector operations, right? uh, yeah, and definitely a dynamic path constructions by the construct arc. So rather making wasting too much time here, I actually am just going to very deep dive into the mathematical things. But yeah, now a lot of interesting things we'll see by the symmetry in this motions of artistic patterns of various mathematical curves. So actually, I was motivated one by working on such things that creating symmetry. These books that creating symmetry and the artful mathematics of wallpaper patterns. So here we actually by the help of this book and referring these books, I am and also through the lens of art programming, uh, my work is to uh, uncover the hidden symmetries and patterns that adorn the walls of fabrics around the world. And that's how we take some complex exponentials and the rotation in the complex plane. So, so here, actually, I'm not going to too much with the mathematics things, but yeah, intuitively what we can understand that what is the I mean, if we just understand the what thing how in complex plane how things work by the representation of rotations, this amp things is like we focus on the amplitude which is the radius of a circle, and this frequency is like the speed and the direction of rotations. It could be positive frequency which rotates counterclockwise while negative frequency rotates clockwise. Okay, these are the things. So this is what we do, and actually, you if you just follow this order, this mathematical decorum to work in your visualization case in complex plane. This is good enough rather than memorizing all this robust mathematical formula, which where we see that R is that amplitude. You can see that amplitude R is amplitude, and or the modulus you can say, and theta t is the phase argument. That is this is what we see the expressions. Okay, and yeah, one thing is that phase, that is the initial angular offset, that is the theta out there. Okay, so yeah, yeah, fine. So now let's I'll try to plot the functions. If you go for the function that's iota, this is what we call the imaginary number or the complex number, that is iota t and zero point 0.5 t times I, which is raised to the power 5t of 1. So here, so all the I times t, this factor here, this guys represents a linear increase in the imaginary directions, which is creating a spiral like effect. If you Okay, so what if I go for the visualization first? You see, this is the visualizations. First, focus on the visualization, that how things get spirals into it, and it is goes like counterclockwise, or you can say anti-clockwise, whatever. So here we can observe the interplay between a linear and the circular components, which resulting in a unique captivating shape. So uh, yeah, I think you'll see that the point 0.5 of these terms, it's because, this part actually. So here, 1 I, so this is nothing but 1 I times t. So this actually represent a linear increase in the imaginary directions and a spiral like effect, and zero point 0.5 into this component adds the additional circular motions, that it's the one dial, this dial is getting rotate, and one another circle is getting over and over and over again. So yeah, and this phase shift into one, and so frequency actually determined by this 5 times t there. Yeah. Now, there's an interesting part is that in the script, you see this R chunks, that we define a t as a sequence of values from 0 to 2 pi, 0 to 2 pi there, and time sequence, and sorry, yeah. So yeah, 0 to 2 pi definitely. And we create a symmetry functions. This symmetry function is known as I times t adds 0 0.5 I raised to the power 5t plus 1. And here, which introduce our additional circular motions with the different parameters. So we plot the functions with the same artistic argument as we do before. And Definitely there is the amplitude. The point 0.5 is nothing but amplitude. 5 is the frequency and phase is the 1. So these are the initializing the parameters out there. And here we generate the complex functions with the given parameters, right? And it's a very simple way to save these animations, or maybe you play these animations in your visual library, display sections of your R chunks, and I mean the R interface, R studio interface. And we try to combine this multiple circle. So formal algorithms is says that we define the amplitude, frequency and phase of the component circle. Frequency congruence, yeah, I mean frequency congruence means that mathematically it is expressed as the frequencies being congruent modulo n. Okay, so I'm not going to a very mathematical things because maybe some of you may not be understand such a thing. So yeah, we also define the functions for generating the circle of complex plane, some of the circles which compute some component circles. When I plot this resulting functions and step in the code. So first is to define the circle functions, where the t is a sequence from the 0 to 4,000 points. We take the circles at I mean, three different points. Yeah. So we use the plot function to visualize the real and imaginary parts of Z, so with appropriate settings of axis and notation, line types, and etc. Okay. Yeah. And yeah, this these are all what should I say? Uh, so this is a you know mm, actually it's a four folded rotational symmetry we follow. So this symmetry arises due to a specific mathematical property which is related to the frequencies of the components. So yeah, these things are discussing beyond a scope, but if you have any further questions about that, you may ask, and I would like to answer such a questions because. But okay, we can explore this again. Uh, so such thing is quite interesting. Yeah, I hope here I'll give a scope that to show this thing, the meaning of these things. So let's see, let's explore. Okay, well, so you see these visualizations out there. So here, if you go to the coding part, here this circle actually generates a circle to complex plane given the uh, amplitude, frequency, and phase. Uh, and sequence that is 0 to 4, and we create the sequence of 1,000 points between 0 to 4. And this is interesting. Yeah. Now, this creates a base circle. So actually, these things create the base circle. Okay. And this is interesting. It adds a circle with a different amplitude and frequencies. And this is another circle with a different amplitude and frequency and phase, right? Now we plot real of z values. I mean, we try to plot the real of z values and the imaginary z values, plots the real uh, part rez against the imaginary part of imaginary z, and we take the axis as a false because it removes the axis, and false, these things removes the annotations like axis levels and titles. Type L means I insert the plot, it's drawn the continuous line, and LWD, these parameters are these arguments is the line width for better visibility, and ASP1. This maintains the aspect ratios. Okay, aspect ratios, which ensures the plot is not distorted. Okay, so this code will produce a plot that visualizes the combined effect of three circles in the complex plane, uh, revealing the intricate patterns that uh, emerge from their superpositions. And yeah, that's how the beauty looks like. Yeah. Shamrit, can you tell me, are we running out of time? How many times we are still left with?
Yeah, it's 1 hour already.
Okay, okay. So
Mm.
I would like to take 15 or 20 minutes more, and maybe rest of things as it is, uh, three. I mean, up to three, right? So I mean up to eight, as my UK time is 2:36. Yeah, so it's up to three. Okay, okay, fine. So here is the mathematical things out there. So I have already told you these are things, and yeah, here again, this circle. I'd like to go for I mean, the circle function, which models a component of the complex exponentials. Okay, so here is our the component out there, and same algorithms will follow. And following such algorithms, okay. What is a interesting fact out there that we yeah, sorry. So we go for the, I mean, despite of having the different frequencies, the use of congruent modular arithmetic, here you will see that we use of congruent modular arithmetic to ensure certain symmetries in the ruling pattern, resulting patterns. So for instance, if you take the inclusion of negative frequency, still maintains a fourfold of rotational symmetry, because negative 7 mod 4 is 1. Okay. So the insight behind the animation is constructed to visualize how complex functions evolve over the time. Okay, so if frame generations of 500 of frames, it could be, yeah. Here, this cum sum things is a function that calculates the cumulative sum of the circle components up to the current times of point j, sorry. So these are the thing you have to remember while something. Algorithms and all these things is governed with the three things. That is the amplitude, frequency, and one is phase. Okay, so remembering all these things, we can plot such a things and make some visualizations. So we focus here. We focus on three. Some of the components. That is the frame generation, algorithmic approaches, frame generations, plotting the path, cum sum, GIF creations. So code behind the creation of this presentation is that if you see such an animations out there, or the thing is that it's a I mean uh I mean if you just see the code, this is a code actually effectively say demonstrate the rich interplay of multiple circular components, right? So yeah, if you just go back to the algorithmic approach of frame generations, or maybe the things which are covering that with the code of visualizations, we can focus three things. That is the plot, frame generation, that we take the 500 frames and sequence which each frame corresponding to a different time point of j, and for each frame the complex function of z is calculated, and the positions of the current point along with the path is plotted. So yeah, and this cum sum, we further see that function which I have already told, that calculates the cumulative sum of the circle components. Okay, so yeah, so here, if you go for the, trajectory animation cases, which each frame displayed a uh, 1 divides 30th of a seconds. Okay, So the result is a smooth animation. You'll see. Sorry, it's a quite a smooth animations, and that traces the trajectory of the combined complex functions as well. So yeah, mm, here this is one of the beautiful things out there. This is a butterfly curve. You'll see. And this is also one of the wonderful representations of uh, such a complex things. So the mathematical elegance is that the parametric equation, which is express the coordinates, the points, making up a curve as a function of a parameters. Okay, so we these are radius functions, and we take the functions as like this with some something the formulation look like this, and this equation define how the coordinates at x and y points the butterfly curves. One thing is that parametric equation for x and y, and yeah, so the key component of this code is given here. So I'm not going to explain all these things because we are running out of time. And yeah, the symmetry of butterfly curve is something different. So it's a characteristic feature that arises the even and odd functions, periodicity, definitely as sine cosine functions are there, and definitely one of the finest things now I'm going to say. So maybe this perhaps this is the we are quite a end of these things. So yeah, this is a mirror rows. So mirror rows actually it's a rows curves, you can say, or where the points are plotted out order of rows curves. So we apply the technique of more complex mystery curve. So this is a mathematical foundation of the Moore rows. So So you see that all this r theta is a radius of the function of the angle theta, and a is a scaling factor. So, or yeah, and k is the positive integer that determines the number of petals in the rows. So if we see, okay, now I'm just removing all this mathematical part. And if we go to define the problem of the mirror rows, that our objective is to generate a mirror rows pattern by connecting the points of the rows curves. So what do we input? We take the input of number of petals in the rows curves. We take the number of uh, points or the degrees for the calculations, and delta theta, you'll see this del theta is an angular increment between the consecutive points. And what you get output, you get a typical plot graph or animations of mirror rows. It's a which is a visual representation. So we set up the environment, uh, and you know we import necessary libraries like ggplot2, ggAnimate as well. There you can see. So this is a rose curve formula equation, that's r theta and sine cos things. Uh, so yeah, these are the things that we take it to Cartesian coordinate, convert to Cartesian coordinates. So we use a polar to Cartesian. So here things are not like Cartesian to polar; it's a polar to Cartesian. Okay. So yeah, now yeah, here the visual representation comes here. Okay, so you'll see that how things look like. So here our objective. Okay, so what if I go for the writing these things? Okay, so oh sorry. So yeah, so the del theta is angular increment, as I say, the del theta and angular increment it's a static thing, so I can change alongside. And n is a 360 things, the number of points for the calculation, and k4 is the how many petals we want to see. So you can change accordingly, or maybe as it is a dynamic, I mean, the program is a little dynamic, you can use your own, I mean, sorry, static. So you can use your own dynamic way to uh, see the visual. So I have taken one by things as a one by one. Okay. So yeah, yeah. I mean, someone is. And we sorry. And that's how the writing code actually. So it's all about like initializing the plotting area and set up to the environment with equal aspects of ratios. We connect x and y points sequentially to create the mirror rows. And yes, this k equals to 1, and these sort of things you will see here. So this k is a very small or the larger del theta we see while it's case up to h cases. And for the case of different programming interface, things lies same, it doesn't change. So basically our context comes into those sort of things only. Okay, so the thing is like, oops, yeah, just let me see. Yeah, only these sort of things. So it's like angle del theta, how, and you'll see a thorough you know a demonstration that how you can change your angles parameters and this. So once you will understand this analogy behind this, so the code, writing the code is just uh, is not a very easy, I mean difficult with you at all. I'm sorry. So I'm not finished yet. So yeah, so now we'll see some of the hidden unraveling symmetries out there. So which is this the artistic fact with the and mathematical stuffs out there, and you'll see this animations out there. So it's a this is what the I mean that mathematics and artistics interplay out there. So so with the same notions and same viewpoint, we merge the mathematical precisions and artistic creativity and demonstrating how altering a parameter can lead a vastly different, uh, um, you know, uh, what I supposed to say that is, uh, and it's a in such a sense that a technique that is you merge mathematical precision with artistic creativity and demonstrating how altering a simple parameter and that can lead to a vastly different and visually compelling outcomes. So again, the same things, the same viewpoint at the code. I mean, there's a little bit change out there, but idea behind that is quite simple. So the three fundamental things comes here, the three fundamental components out there, that is the amplitude, frequency, and phase. So it's all about the playing with these three parameters. Nothing changes out there. Okay. So yes. So actually, here we modulate and amplitudes of the components with time. We can change the shape of the curve in a very dynamic way, and to note that it's an example using uh, the Gypsy pattern. So you can also see how this things are changes, and even you can see here some of the things. If you if I go to the code part, you know. So yeah, Mhm. So here, this call HSV, these things is to choose the hue, which is we use for the saturation of the value of each points line. Okay. So this is one interesting fact. So you can explore this further. Okay. So you note that this this column out there. Sorry, 1 second. I just having some batteries gets down. So I have to put this. Yeah, yeah. Thanks. So yeah. So the you note one things that call equals to and rest of the things. It's to set the colors of the points and lines. So used call HSV here. Yeah, these things. So it's like choose the hue or hue means the saturation value of the each points and lines. So finally, we can change the frequencies, amplitude, and phase in sync to arrive at these animations. Okay, couple of other nuisance in this code we also gave. You can see that in here that the lines which is produced by the lines, okay, and this. So lines cannot be different colors. So here I use the segments instead. Okay, the segments for real of z values and imaginary z values and z2 for the z2 as well. So these are the fundamental stuffs you have to remember. It's not a very quite a difficult. It's all about to exploring your ideas, playing with mathematical functions, and that how the dynamics keeps changing. Yeah, it's so the so here it's all about demonstrating beauty with complexities, and my aim is to create medium bridges between mathematics and art with the help of R R program, and definitely it could be a great educational tool for teaching mathematics as well. Yeah, new avenues for research and canvas for creativity. We can explore art in this essence. So here are the few references. I'll share these things with you guys. You can see and explore this. Actually, my entire presentation is made with based upon these blogs which I used to write. Yeah. So thank you for your time, and yeah, I'll see you guys for the next mathematical explorations are. So yeah, I'm all done. So yeah, I'm going to stop share the screen, and yeah, I
Thank you very much for your wonderful session. It is very knowledgeable.
mm,
There is one question in the chat section for asking GitHub something. So I think you should answer this.
sorry, who's yeah. Uh,
GitHub
so
repo. So do you have the GitHub?
you will have a GitHub repo, right? Yes. I mean, which GitHub repo is asking here is Nitin. So what in which context GitHub you are asking? So sorry, like
So can you please unmute
I
yourself
mean,
and ask?
yeah, he can unmute.
He is not there. No, no, he is not there, I think.
Excuse me,
Yeah,
sir.
actually, yes. Tell me.
Good evening, sir.
Yeah. Good evening. Good evening.
Sir, myself, Vikramjit, and I have some questions regarding your presentation. Can I ask them?
Yeah, yeah, sure.
Sir, I wanted to ask about that recommend sequence you talked about.
Mm-hmm.
So, in during the code, you said that we use points from 1 to 179.
Mm-hmm.
using the semicircle construction. So
Mm-hmm.
I really needed to ask that why not 1 to 180? Because for semicircle it is 180 degrees, na? That's why. So why only 1 to 179?
Yeah, actually, it's like it's a vector perspective. Okay, it's a vector perspective. Like so you're starting. It's not like a taking digits. It's a initializing the vector. Okay, so if it starts from the zero, so we are taking actually all the 180 steps from 0, 1, 2, 3. Okay. Do you know the idea of array and vectors in a programming context? So it's like a initialing 0 to 1. I mean, to take the 180, you have to start from the 0. From 0, yeah. So
Sir,
that is the, yeah.
sir,
So,
the doubt is this, that when we take from 1 to 179 na, so
hmm,
we get 178 points, because 179 minus 1 is 178.
mhm.
So 2 points are still missing if we consider the vector perspective we are talking about.
So, okay.